Welcome to The Explainer. You know, when we think of the digital age, stuff like cloud computing, endless streaming, massive AI models, we usually picture invisible data just floating in the ether, or maybe some sleek, glowing microchips. But the physical footprint of the internet, it runs incredibly hot. I mean, inside a data center, server racks can literally reach temperatures hot enough to bake a pizza. So today, we're putting a massive spotlight on the unsung hero that's actually keeping the internet from melting down, the condenser. We're going to break down exactly how it works, nice and easy. Okay, so here's the central mystery we're solving today. Where does all the heat from our cloud and AI servers actually go? Because every single time millions of us are simultaneously asking an AI chatbot a question or, generating a high-def video, the physical servers doing all that intense math generate scorching physical heat. And obviously that heat cannot just stay trapped inside the building, right? Or the hardware would instantly fry. It literally has to be captured, moved, and physically thrown out of the building. And the device pulling off that crucial magic trick, that's exactly what we're exploring. So here's our game plan for today. We'll start with the core of heat rejection. Then we'll look at how condensers actually work. Next, we'll compare water-cooled versus air-cooled systems. After that, we'll check out the guardian of efficiency, ATCS. And finally, we'll wrap up with some sustainable condenser trends. Let's get into it. All right, Section 1, the core of heat rejection. Let's dive right into this. To really appreciate the condenser, we've got to understand the neighborhood where it lives, which is the refrigeration cycle. Basically, every cooling system running a data center relies on this continuous four-step loop, and it's all driven by a chemical refrigerant. So step 1 is the evaporator. It acts kind of like a sponge, just soaking up the blazing heat from the servers and turning into a gas. Then step 2 is the compressor. This is basically the system's heart, powerfully squeezing that gas until it's super pressurized and actually hotter than the outside air. Step 4, way at the end, cools things back down. But look right there at step 3, the condenser. This is our focal point for today. This right here is the ultimate exit door, where all that collected heat finally gets thrown out of the building. Moving on to Section 2, how the condenser actually works. So the fundamental physics inside a condenser really come down to two simple words: heat rejection. Remember that blazing hot high-pressure gas coming out of the compressor? Well, the condenser's entire job is to steal that heat and just throw it away into the outside air or into cooling water. And as the heat leaves, the refrigerant gas physically transforms. It condenses back into a liquid. Think about steam hitting a really cold winter window and turning back into water droplets. It's the exact same concept. And this phase change, it's the secret sauce. Because only as a liquid can the refrigerant travel back inside to absorb more of that server heat. Without the condenser throwing heat outside, the whole loop just stops dead in its tracks. Let's head into Section 3, water-cooled versus air-cooled. Now, what's really interesting here is how exactly we reject that heat. Data center engineers basically have a massive choice between two main approaches. On one side, you've got water-cooled shell and tube condensers. Hot gas hits tubes filled with cold water. Now, because water is absolutely brilliant at absorbing heat, this gives you unmatched energy efficiency. But it demands massive amounts of water. On the flip side, we have air-cooled fin and tube condensers. Picture a giant car radiator just blasting outside air over the tubes. The huge win here? Literally zero water is required. But the massive drawback is that when summer hits, say 35 degrees Celsius, efficiency absolutely plummets, and those power bills skyrocket. Okay, moving right along to Section 4. The guardian of efficiency, ATCS. For hyperscale data centers using those water-cooled systems, maintenance is incredibly high stakes. Let's shrink down to the microscopic level for a second to see how they protect their investment. Look at this number, 0.3 millimeters. That is roughly the thickness of just a few strands of hair. In a water-cooled condenser, outside water is constantly carrying minerals and dirt through the tubes. If just 0.3 millimeters of scale builds up, it acts exactly like a clogged artery. The condenser just can't shed heat properly, the compressor has to work overtime, and energy efficiency drops by up to 15%. In a giant AI facility, that tiny layer of dirt literally wastes millions of dollars in electricity. So enter our microscopic superhero, the Automatic Tube Cleaning System, or ATCS. It's essentially this army of tiny scrubbers working while the servers just hum along. First, the system injects hundreds of slightly oversized sponge balls right into the cooling water. Second, the water pressure rockets these little sponges through the tubes, gently scrubbing away that scale before it ever has a chance to harden. Third, a specialized strainer catches them all at the exit. And finally, they are collected and ready to recirculate. It's kind of like a microscopic game of Pac-Man, just happening automatically dozens of times a single day. Now, this continuous cleaning is absolutely essential because data centers literally never sleep. You can't just turn off the cooling to manually brush out the pipes. ATCS guarantees zero downtime and keeps everything at peak efficiency. But here is a quirky fun fact for you. Facility managers have to constantly monitor the wear and tear of these sponge balls. Because they're endlessly scrubbing, they do eventually shrink. And if they get too small, well, they'll just swim right through the tubes without ever touching the sides, which completely defeats the entire purpose. All right, let's step back into Section 5, Sustainable Condenser Trends. Keeping the inside of the tubes clean definitely saves power. But what about the impact on the outside world? Let's zoom way out for a moment. The modern engineering dilemma in data centers is essentially a giant seesaw between two key metrics. On one side is PUE, or power usage effectiveness. The ideal score is 1.0, meaning zero power is wasted on cooling. And on the other side is WUE, water usage effectiveness, where the ideal score is 0, meaning absolutely no water is consumed. Here's the massive problem we run into. If you use highly efficient water-cooled condensers, your power use drops, giving you an awesome PUE. But your cooling towers evaporate millions of gallons of water, severely spiking your WUE. On the other hand, if you switch to air-cooled condensers to save the local water supply, getting that amazing WUU of 0, your compressors have to work so much harder in the summer heat, completely ruining your power efficiency. It is an incredibly difficult trade-off to manage. But engineers are innovating rapidly to conquer this PUE versus WE dilemma. Let's look at 3 cool trends. First, microchannel technology. This replaces bulky copper tubes with flat aluminum ones. It shrinks the condenser size and actually reduces chemical refrigerants by up to 40%. Then there's adiabatic cooling, which is honestly the ultimate compromise. It runs totally waterless 90% of the year. But on those brutally hot days, it sprays a microscopic mist of water just to pre-cool the air. It basically allows the condenser to sweat like a human to cool down. Finally, we have high-chilled water systems. This involves designing the actual servers to tolerate warmer water temperatures, which means the condenser doesn't have to work nearly as hard in the first place. The digital realm we all live in relies on some of the most intense physical thermodynamics on Earth. The condenser might just look like a giant metal box from the outside, but it is truly the critical exhaust valve of human progress. So, as AI models grow exponentially larger and hotter, how will the physical engineering of these colossal structures evolve to handle the heat? It's a massive challenge, and one that's going to shape our physical landscape for decades to come. Thank you so much for diving into the world of the condenser with me today. Keep learning, keep questioning, and I'll see you on the next explainer.